Introduction to Motor Deceleration Controls. In this presentation, we're going to be looking at why are deceleration controls necessary and types of electric motor deceleration techniques, more of a listing. Now, deceleration is an extremely long word. It has far too many syllables, as most experts agree. It's much easier for us to simply use the word braking, but let's face it, deceleration makes us sound smarter. Now, it's good to know that in the electrical field, depending on the application, when a motor is de-energized, the mechanical load may cause the motor to continue rotating. Now, at times, this can be quite dangerous. And if we look at this, where we have a motor that is lowering a crane cable winch, and the motor is on, and now we're going to turn the motor off, notice that it keeps turning. The vertical tension due to the suspended loads when applied to a cable reel will cause the reel to rotate as the load drops. And so obviously a system like this for a crane or winch would not work very well. So we have all sorts of different types of cranes and winch systems, from really massive mine hoisting winches, where we have massive brakes on them to ensure that nothing moves after we've stopped the motor, to things like elevators, as well as the standard mobile overhead crane system. All of these motors need a means of ensuring that the motor does not rotate when we have stopped turning the load. Another application is on things that have horizontal inertia. When we have a conveyor like this, the horizontal inertia of the load on the conveyor will cause the conveyor belt to continue rolling after the motor has been de-energized. So if we look at that again, what's happening is we turn the motor off now, but the belt is still turning. And so that's really a challenge when it comes to getting precise locations or precise movement of an object on a horizontal belt. However, when we get to inclined belts, there is an additional hazard. So something like this, a really large conveyor system, we really need to ensure that the conveyor will not move if it's ever shut off. Because if it's on an inclined plane like this, if it were to shut off and it was loaded with all sorts of rock and soil or whatever else, the loss of power while the belt is loaded would result in the belt reversing direction and gaining uncontrolled speed. The aggregate load would then be deposited at the start of the conveyor belt, just pile up, and that would be extremely dangerous. Another place that we use braking is when we have heavy, dense, large diameter mechanical loads, which gain significant inertial energy when spun. After being spun up to high speeds, it could take significant time for the load to coast naturally to a stop, seconds, minutes, even hours, which is kind of ridiculous. It's considered a waste of time, right? And the efficiency of the process would have to be elongated because you have to wait for this silly thing to stop turning. And of course, there would be an increase to the potential for worker injury. And so what we have a picture of here is a paper roll at a paper mill. And the process, very simplified here, is they take the parent roll and they feed it through a bunch of different rollers and they get the precise thickness that they want and they start rolling that. But it is a fast process. So upwards of 2,000 meters per minute, you need to slow that thing down as soon as it's at its full diameter and stop it, because you need to then quickly move it off and start the process again. And so things like this need to have braking systems to quickly bring it down in speed so that we can then have it stationary and transport it to a new location. This is also the process that would take place with things like steel coils when that's being manufactured. Same idea, very fast speed. For efficiency, they need to stop it very quickly in order to facilitate transportation. Another application of braking is in wind energy generation. It requires braking systems to ensure that extreme wind events during low electrical load periods does not exceed the assembly's RPM rating. Otherwise, significant damage can occur. And to put this in perspective, what we're talking about here, if there's very little electrical load on an alternator, the prime mover would not be working very hard, would it? It would be sort of coasting. But in this situation, we have the prime mover being the wind. And if the wind is pushing very hard and there is no electrical load. That means there is almost zero counter torque being applied by the generator because it's not supplying any electrical load. It's very easy to spin the rotor. And with an extremely high wind event and no braking in a no load condition, we can get dangerously high speeds, which we can see here leads to the catastrophic destruction of the wind generating assembly. So there's braking assemblies used in all sorts of different areas of the electrical trade. Now, the types of electric motor deceleration that are commonly used are listed below. We have friction, plugging, dynamic, regenerative, eddy current, and finally, electronic drive control systems, often referred to as speed control or variable frequency drive systems.